Okay, in this section I'm going to show you some examples of compound interest. And before we get started, make sure you read the formula and go through the hard copy. But let me remind you a few things about where this value I comes from. I is when you're compounding, you have an annual interest rate and you have a rate per period. And so to get the rate per period, you take the annual interest rate and divide it by M. So down here, you'll see I have 12% for an annual rate. We're compounding monthly. So if you want to find the rate per month, you actually divide that rate by 12. So notice I converted it to decimal. So it's 12% divided by 12 is actually 1% or 0.01. If you have 6% compounded quarterly, then you take 0.06 divided by 4, and that gives you 0.015, which is 1.5%. Now, if you have 4% compounded daily, and we're going to use 365, so what you would do there is you would just leave it in this form. You wouldn't really try to convert it to a decimal value. Just leave it as 0.04 divided by 365, and that would be your daily rate. So this is your daily rate, this is your quarterly rate, and this is your monthly rate for the three examples. Now also make sure you understand that N is the total number of compounding periods. So what you have to do is you have to take the number of compounding periods per year and multiply it by T, the number of years, to get N. So in this example, we're compounding monthly for 8 years. So M is 12, so N would be 12 times 8, which is 96. Here we're compounding quarterly for 50 years, so M would be 4 for quarterly compounding, but since it's 50 years, N would be 4 times 50, which is 200. And then for this one, 10 years compounded daily would be 10 years at 365 days a year. We're ignoring leap years in this example. So we have 365 days a year times 10 years. That would be 3,650 compounding periods. So just keep that in mind as we work these problems. I'm going to leave these for you to read, but make sure you read these examples so that you understand the difference between lump sum investments and annuities. So on the left I have lump sum examples, and on the right I have annuity examples. And we don't cover annuities in this section, but I wanted to go ahead and make it clear to you the difference between lump sum and annuities. Okay, in this first example, notice that the grandparents deposit a lump sum amount, not an annuity, it's not monthly, but it's a lump sum amount of $6,000 into an account, and we want to know how much money will be in the account 17 years later if the account earns 9% compounded monthly. So now we have compounding, but it's not an annuity, it's a lump sum investment. So since we want the amount, we're going to use this formula, A equal P times 1 plus I to the N. We're given the principal is $6,000, that's the amount invested. We know the time period is in years, 17 years. We know the rate, the annual rate is 0.099%. We're compounding monthly, so M would be 12. Well, since we know R and M, we know I would be 0.09 over 12, which is actually a terminating decimal, 0.0075. And then N would be 12 times a year times 17 years, which is 204. And then we're trying to solve for the amount. So if we plug everything in, we get 6,000 times 1 plus 0.09 over 12, or you could just say 6,000 times 1 plus 0.0075, and then we're going to raise it to N, and remember N was 204, that's a total of 204 compounding periods. So when we put this in our calculator, if you put it in your calculator pretty much just like this, you have to use the caret for the exponent probably, but you'll get $27,551.32. And if you wanted the interest earned, just subtract 6,000 from this to get the interest. Now, the importance of decimals is huge here. Let me just show you real quick. I'll let you read this, but let me just explain something to you. If the interest rate had been 8%, that should be an 8, not a 9. If the interest rate had been 8%, then you would have I equals 0.08 over 12, and you'd want to leave it like that, because 0.8 over 12, all you can do is approximate it as a decimal, since it's a repeating decimal. So let me just show you. If you do it the right way by leaving the rate as 0.8 over 12 in here, so you have 6,000 times 1 plus I raised to the n, you get $23,271 and change. But if you were to round this to 0.0067, then you're going to get $23,429 and some change. So you basically have overpaid your client $150 there and lost your company some money, and so you might get into a little bit of trouble on that. So make sure you understand it's important to you only write it as decimals if they're terminating decimals. So this one was not a terminating decimal. 0.08 over 12 is not terminating, so I need to leave it in its proper form, 0.08 over 12. If you have a compound interest problem and you're trying to solve for the principal, you can actually use either one of these two formulas. Principal is the amount divided by 1 plus I to the n, or principal is the amount times 1 plus I to the negative n. So in this problem, it says how much should you deposit initially. This is a lump sum deposit into an account paying 10% compounded semi-annually in order to have $1 million in 30 years. So in part A, we're given that the rate is 10%, which is 0.1. The amount we wish to have is $1 million. Time is 30 years. Semi-annually means we're compounding twice a year, so therefore the rate per semi-annual period would be 0.1 divided by 2, which is 0.05. N would be 2 times a year for 30 years, which would be 60, and we're looking for P. So if we put all that into one of these formulas, I use the second formula first here. So if we put the amount, which is $1 million, in here, and then 1 plus I, remember I was 0.05, so I have 1 plus 0.05 raised to the negative n, which would be negative 60, and then I'm going to get $53,535.52. And this is just another way to do it. If you want to use that first formula, when you divide, you use a positive exponent in the denominator. Then it also says what happens if you compound monthly or compound daily. So basically I did the same formulas. If you compound monthly, all that changes is it changes I. Instead of 0.10 divided by 2, it's 0.10 divided by 12. And it also changes n, because 12 times 30 years would be 360. So you would make those two changes, and then you get $50,409.83. If you do 365 or daily, then this becomes 0.10 divided by 365, and then this becomes 365 times 30, and so that's where I got 10,950. And when I plug that into the calculator, I got 49,807.53. Now you can also have what's called continuous compounding. Well, with continuous compounding, that means you compound infinitely many times a year. You get this formula for the amount, and then you can solve for that formula for this formula for principal. So if we had continuous compounding, we would simply take the million and put it on top, and then on the bottom we would have e to the 0.1 times t. So that would be e to the 0.1 times 30, and then we would put that in the calculator and we get 49,787.07. And notice that, you know, there is a limit. Obviously, you can't just deposit $5 and it grow to $1 million, no matter, you know, how often the money is compounded. Okay, pause the video and read this problem, and I'll just tell you what we're basically trying to find. We're actually trying to solve for time in this problem. We want to find the number of compounding periods In other words, the number of compounding periods we need so that we're going to take a principal, we're going to use this formula, and we're going to take a principal of $7,000 and we want it to grow to an amount of $10,000, and we know I is 0.0225 because the rate is 0.09, but we're compounding 4 times a year, so the rate per quarter would be 0.0225. So first thing I'm going to do is divide 7,000 into both sides, and then I'll reduce the fraction. So 10,000 divided by 7,000 is 10/7. And then I can actually add these two numbers together and get a single value, 1.0225, to the n. And now we can take logs of both sides, so I'm going to take the natural log of both sides. And so the natural log of 10/7 is going to be on the left, and then I'm going to take the natural log of 1.0225 to the n on the right. And then it turns out there's a log property that says if I have the natural log of 1.0225 to the n, that's the same as n times the natural log of 1.0225. And now that's just a number times n. So if I divide both sides by this log, so divide both sides by the natural log of 1.0225, that will give me n. Now n turned out to be just a little bit over 16. Well, that means that 16 quarters is not enough. That means I got to go over 16 quarters, and since money's not going to be compounded between quarters, that means I have to bump it up to the next highest quarter. So I actually have to bump it up to 17 quarters on that problem. Sometimes it's difficult to compare investments, but if you calculate the annual percentage yield of two investments, you can determine which is better. And I'll let you read the literature on the APY that's in the notes. But basically, this is the formula to calculate APY. So if you're given 9% compounded monthly, then here you know R is 0.09 and M is 12. And so we can calculate the APY by just saying 1 plus 0.09 over 12 raised to the M. So that'd be raised to the 12 minus 1. And I got 9.38%. Over here the rate is 9.1%, but we're compounding quarterly. So when I get the APY here, I have 1 plus 0.091 divided by 4, quantity raised to the 4 minus 1, and I got 9.42%. So this would be the better investment because it has a better annual percentage yield. And so, you know, this is how you compare investments. The reason these are difficult to compare is because here the compounding is better because you're compounding monthly, but over here the rate is better. So it's hard to know which one in the long run is going to be better off. But by doing this APY formula, we can see that the second one is the better investment. Okay, pause the video and read this, and then come back to where I start talking about the solution. Well, this is a two-part problem. The first part is a simple interest problem. He's got to pay his friend back. You just use P times 1 plus RT, and you get that he's got to pay his friend back $5,503.33. And then his friend's going to invest that money at compound interest rate, and here's the annual rate compounded quarterly for 5 years. So I would be 0.063 over 4, and N would be 20. So the amount would be, the amount here we're using the compound interest formula would be 5503.33 times 1 plus 0.063 to the 4 raised to the 20, and that comes out to $7,522.50. Number 6 is just a fun problem. I'll let you read it. It's pretty straightforward, but it shows you the power of compounding over long periods of time. Now number 7, I'm just going to drop to the solution here. If you solve this formula right here, divide both sides by 250 and you get 4 equals 1 plus R over 12 to the 48. Then you have to actually take the 48th root of both sides. So you can Google YouTube on how to do that. And then what you have is the 48th root of 4 equals 1 plus R over 12. And then you can solve that using algebra. Just subtract 1, then divide by 12 to get your answer, 3.52 Good day.